So one of the things that you are going to be doing in your CPT is you're going to be making a circuit. So why don't we make one together virtually, and then you can just kind of follow along, all right? So one of the things that you have to do, if you look at the CPT, so if I go back to the CPT, is it says build a simple circuit with one battery, one light bulb, and some wires, okay? And then draw an image of your setup. Now I should mention the setup should have using symbols. This is actually important, okay? So using the symbols, explain that. So here we have the images, but we can actually draw them as with symbols like this, right? So this would be the battery. This would be a wire, for example. This would be a light bulb, which we can connect to the wire. And then this would be the wire that connects back to the battery. So there is, for example, a simple circuit. Okay, so when you're drawing the setup, use the symbols. Okay, but for what I'm going to show you, I'm just going to use the visuals because it's a little bit nicer to look at. Okay, you can actually switch in between; doesn't matter. So once you build it with the symbols, you can go back and forth between the images and the symbols. So here is a simple circuit with actually let's make this look a little bit better. Hold on. Let me cut this. Let me cut this. Okay. Let's see. And let's make this a little bit nicer to look at. So you can kind of really nicely see the flow of okay. All right, so here we go. So there you go. It's a little bit nicer. Still not really that good. But anyways, you can see we were talking about last time what current electricity is. It's the flow of electrons in a closed path. So, the minimum things that you need to make this work is a battery, wires, and something to use up the electricity, okay? So one of the things you're gonna do is make a circuit, but show me with the symbols, okay? So there you go, there's an example of this. And I am recording this, so if you forget, you can always just go right back to this. Now, then what you're gonna do is you're gonna be asked to take some measurements. So you're going to be asked, for example, calculate the voltage and calculate the current. Actually, you're not going to be calculating them. You're just going to be recording them. We're going to actually just be calculating the resistance. So let me show you what I mean by that. So if you remember, let's go back to this. We could put in a voltmeter. We can measure the voltage of my circuit. And so this is about 9 volts. Now I can test that voltage, see if that's the same everywhere. So for example, I can move my probe here and here, and you'll notice that I get 9 volts. So what it looks like there's 9 volts of current, sorry, 9 current. There's 9 volts in this circuit, all right? Now, I could use my ammeter. So last time I didn't see this, maybe my vision's going, but this is the instrument that measures current. So if you remember, the voltmeter measures the voltage, and it's collected in what's called a parallel pathway. Now, why is this a parallel pathway? Because if I take a print screen of this, and I put it in Paint, and I paste it, what you can see is the flow of electricity. So here is the negative end. So we have electricity flowing from the negative end through my light bulb and back to the positive end. But I can also see electricity is following a separate path that's going through this wire into my voltmeter, and then through my voltmeter, and then back. So because it has more than one path, this is what's called a parallel circuit, and a voltmeter has to be connected this way to work. Whereas the ammeter, I'm going to show you right now, is actually connected differently. So let me hook up an ammeter so you can see what I mean. So let's say we want to connect the ammeter, which measures current. Actually have to connect that in series. So what that means is I'm going to connect it like this. Oops. Let me move that so you can actually see a little bit better. Okay, now watch this. Okay, now if you look at the way it's the electrons are flowing, there's only one path for the electrons. So this would be an example of a series circuit that includes a light bulb and an ammeter. So let me take a screenshot of this so I can draw it out for you and put it in paint. Okay, so with the ammeter, we're connecting it in series instead. So again, take a look. You have, this is the negative end. Electrons are coming out of the negative end, going through the light bulb. They're coming through the light bulb. They're going through my ammeter. They're coming out of the ammeter and then going back to the light bulb. So there's only one path available. So that would be a series circuit. Okay. One of the things you're going to be asked to do is to measure the voltage and the current in your circuits. So from the example that we looked at, we have a current of about 0.9 amps. And the voltage, if you remember, the voltage was 9 volts, right? So if you remember, we can now use Ohm's law, and we're going to do some more Ohm's law calculations today. We can now use Ohm's law to figure out what the resistance is. Okay, so that's one of the things you'll be doing in your circuit. You're also going to be asked to put light bulbs in series. So for example, if I follow along and I go to the next section, it says connect 2 light bulbs in series, but then it also says to connect 2 light bulbs in parallel. So let's do that together. And that way you know kind of how to do that. So let me remove the ammeter. Get rid of this. Move this out of the way. So if I want to connect 2 light bulbs in series, what that simply means is I'm going to have 2 light bulbs where there's only one path for the electricity. Okay? Like that. Now, what I can do is I can measure the voltage to see if that's changed. You'll notice that the voltage is the same here. I can check the voltage at the light bulbs. I can put my probes here and here. You'll notice that, oh, that's interesting. Notice the voltage is not 9 here. It's 4.5. I can put the probe here and here to see what the voltage is at this light bulb, and you know, it's also 4.5. That's really interesting. So the voltage out of the, coming out of the battery is 9 volts. We just saw that. It's 9 volts. Right? There's 9 volts. But the voltage of the light bulb is actually not 9. It looks like it's exactly half of that. 4.5. That is interesting. Okay. Now, that's a series circuit with 2 light bulbs. I can then also put in my ammeter. Remember, the ammeter has to be connected in series. So I can, make this a little bit bigger. And I can connect my ammeter to this. And it's showing that the current is 0.45 amps. Now, before, if you remember, the current was 0.9 amps. So it seems that the current is going down. In fact, if I look at the animation, I hope you notice this. Remember, the current is the rate at which, like, I use the analogy of water flowing. So in this case, it's not water flowing, it's the flow of electrons. And you'll notice that it looks like it's slower. Okay, it looks like it's slower. So that would explain why the current has decreased. So this is an example of, again, a series circuit with two light bulbs. And then eventually what you're going to be asked to do is you're going to be asked to make add a third light bulb. So I'll leave that part up to you. Any questions about this so far? So then what we can do is we can actually make a parallel circuit. So remember, a parallel circuit is where you have more than one path. So for example, I can put a light bulb here, like this. So there is one light bulb, okay? I can then add another pathway, like this. Okay. And this would be an example of a parallel circuit. Now, something interesting just happened. I don't know if you noticed that. Let me just actually disconnect this battery. You notice that the flow of electrons, it's moving at a particular rate. You know, when that's the current, right? And when I hook up, and you notice this is a measure of how bright it is. You notice that when I attach this, the electrons are moving faster, and it looks like they're actually a little bit brighter. Again, what we can do is we can check the voltage. So at the batteries, the voltage is still 9 volts. We could check the voltage going through each light bulb. Oh, that's interesting. Look at that. See, that's different. The voltage here is also 9 volts. So it looks like, let me test this one out too. Okay. So there's a big difference there between a series and a parallel circuit. It seems that in a parallel circuit, the voltage is the same as the voltage in the battery. That's interesting. And then what we could do is we could test the current. And I'm just going to use this to test the current, okay? You'll notice that current is 0.9 here. And the current is 0.9 here. And at the battery, oh, look at that. The battery, the current is 1.8, which actually looks like it's the sum of these two, right? 0.9 and 0.9 give you 1.8. So you can see that a series and a parallel circuit, not exactly the same thing, right? There's differences in the voltage and in the current. Obviously, that must mean there's differences in the resistance. So you're going to be playing around with this. You're going to be making your own circuits. But remember, when you draw them out, use the symbols. Okay, don't use the visuals. Do some calculations. For example, mostly it's going to be resistance calculations. And then try to make circuits with 3 light bulbs in series and in parallel. Okay, any questions about, and if you're like, I forgot all that. Remember, I'm recording this, so you can always just go back to it and just follow along, see what's going on. Any questions, ladies? Okay, so then what we're gonna do then is, because one of the things that you have to do in the lab is to do some Ohm's law calculations. So why don't we do a little bit more with Ohm's law, and and then we'll end maybe a little bit early today. Okay. So if you remember last time, we talked about three concepts when measuring current electricity. We talked about voltage, talked about current, talked about resistance, right? And I said current is like the rate at which it flows. Voltage is the strength or the energy, and the resistance is things that slow down the current flow, right? And if you recall, there is a way to mathematically solve this using Ohm's law, the relationship between the three things, where it looks like this, right? V equals I times R, or I is V over R, or R is V over I. Okay, so let's just do a few more questions just to drive home, how to do these. So for example, number one, what would the voltage be if the resistance is 5 ohms and the current is 3 amps? So based on the magic triangle, V is I times R. So that would be 3 amps times 5 ohms, and that's also symbol for ohms. And that would give you 15 volts. So remember, the units are amps for current, ohms for resistance, and volts for voltage. Okay. Here's another question. What's the current if V is 110 and R is 220? So according to our little magic triangle, I is V over R. So I would equal 110 volts over 220 ohms. So that would give us 0.5 amps. Okay. So the format of this is the same as the format for density. When you look at that magic triangle, it's actually the same form. So hopefully this isn't too difficult. Okay. Number three, what is R? R is, if I look at my magic triangle, R is V over I. V over I. So that would give us 120 volts over 10 amps. That will give us 12. Number of the unit is ohms. So you can draw the symbol, or you can write ohms. Okay. What's the voltage if R is 20 and I is 5? So the voltage is I times R. So the voltage is 5 amps times 20 ohms, which would give us 100 volts. Okay. Number 5, calculate I if V is 10 and R is 2. So according to our little magic triangle, I is V over R. Over R. So that would be 10 volts over 2 ohms, which would give us 5 amps. Okay. And the last one is what is R given V and I. So R, again, according to this little magic triangle, is V over I. So that would give us 12 volts over 10 amps, which is 1.2 ohms. Any questions about Ohm's law? Because it is like it's the same form for density, right? Remember, density was mass over volume, and Ohm's law is the relationship between V, I, and R. So, it's the same form in terms of how to calculate these things. It's exactly the same. Any questions about that? Nothing? Now, I do want to go back to Because I'm gonna maybe just mention this today and maybe go into a little bit of detail, and then maybe we could review this, what I'm gonna explain on Monday, okay? So this might make it a little more complicated, but not too much more complicated. If you remember, we noticed something interesting when we added something in series. We noticed that if you add something in series, so for example, you get certain amount of current flow, okay? Now, if I add another light bulb, what actually happens is the current flow slows down and the light bulb isn't as bright. So what's going on? Because if we do a parallel circuit, actually we can put a parallel circuit right beside it so you can see the difference in terms of the flow of electrons. So let's build a parallel circuit. So here's one path. Oops, oh no, I connected the two. Okay, so there's one path. So there you notice. So here, look how much brighter this light bulb is. The electrons are moving faster. We added a second light bulb in series. The light bulbs are not as bright. Electrons are not moving as fast. Now, if we add a light bulb in parallel, so we can have them side by side so you can see the difference. You'll notice the difference between two light bulbs in series and two light bulbs in parallel, okay? So one thing you notice right away, light bulbs are brighter and the electrons are moving faster, okay? The other thing that we notice is that if we, let's say we cut the circuit here, so this light bulb isn't on anymore, but there's still a closed path here. So this light bulb is still working. If we, let's say, cut the circuit here, you notice now that we cut the circuit, both light bulbs aren't working. And that's because the entire loop now is enclosed, right? Here, there's still a closed loop over here. Although this loop is open, this one's still closed. That's important because that tells us that in your home, the way it's connected is actually in parallel in your home. Because if something were to, for example, let's say, you know, an appliance or something, an outlet doesn't work anymore, you know, other outlets will work, right? So obviously the outlets in your home are not connected in series, because if they were, if one didn't work, something happened to one, then other ones would also not work too. They're obviously connected in parallel. By the way, it also explains why when you put too many things, like if you plug in too many things into the outlets, then sometimes what happens is the fuse blows or the circuit breaker goes. So actually we can model that. I think is there a fuse here? Yeah, so we have a fuse. Now, what happens is the fuse, so how a fuse works is quite interesting. A fuse will break if there's just too much current flow. So for example, let me show you what I mean by that. Let's say we replaced this power source with a much stronger battery. Watch what happens to this fuse as soon as I connect it, okay? Boom. So you notice that the fuse broke? Now, of course, this light bulb is still on, but there's just too much current flow, and you'll see like there's a symbol that shows fire. So what's going on? So what does a fuse do? So what a fuse does is actually prevent electrical fires, because what they'll do is they'll stop the flow of electricity if there's just too much current flow. So you can look over here in the top, you know, the current's going like mad. So let's break this circuit. Okay. So watch this. let's remove this. Let's just connect like these, okay? So we're gonna remove this light bulb, okay? Now let's replace this fuse. So you saw what happened. If there's just too much electricity, you're gonna get fire. Now watch what happens here. Notice no fire because the fuse broke. That's actually shutting down the flow of electricity. That's why we have fuses or circuit breakers in the home, is to prevent current overload. The problem is when you have parallel circuits, as you saw, the more that you put in, the brighter things get. That means the more current's flowing through the circuit. That could eventually lead to electrical fire without things like circuits and fuses to stop the flow of electricity. Any questions about that? I mean, you don't have any questions in regards to fuses and circuit breakers, but they're obviously very important. Now, I want to kind of maybe just mathematically explain the difference between the two circuits. So let's go back to, let's remove this. That was a bit of a tangent there to explain what was going on. Let's go back to what we noticed about the parallel and series circuits. So I'm going to hook up a normal battery again and compare these two. Okay, so you'll notice that two light bulbs in parallel, there's more current flow, light bulbs are brighter. And in a series circuit, there's less current flow and the light bulbs are dimmer. So what's going on, okay? Because obviously there's a difference here. In fact, we can measure the current. You'll notice the current going through the battery is 1.8 amps, whereas the current here is 0.45 amps. So obviously there's something going on. There's a big difference between these two circuits. Even though we're using kind of, we're still using two light bulbs and we're still using one battery, right? The hookup is different. That produces a different amount of current going through the circuit. So what's actually going on here, okay? So I'm just gonna mention it, but we'll do the calculations on Monday, okay? So maybe we'll do like maybe one calculation, but then we'll come back to it on Monday, okay? So today's not too long. So when we add things in series, remember that means that you have a battery. So the symbol for the battery is something like this. And imagine that we have a light bulb here. Now, if we keep up with the symbol for light bulb, a light bulb looks like, I don't know if you can see it. I'll draw it actually on the, so it actually looks like this. Okay, so there's a light bulb. And let's see, we put another light bulb here. All right. And we connect it like this. So this is a series circuit, right? Because the electricity can only flow in one direction in this circuit, right? There's not more than one path, right? So what happens is you see the light bulbs are dimmer, and that's because in a series circuit, we add up the resistance. So each light bulb is going to resist the flow of electricity. In fact, that's how a light bulb works, so to speak. An incandescent light bulb would work this way. When the electricity is flowing through my light bulb, the light bulb produces light because the electricity has a hard time moving through the light bulb. And because it has a hard time moving through the light bulb, it gets hot. You may notice this when you plug things into the wall, they get hot, like your charger, because some electricity gets converted to heat. Now, in the case of the light bulb, a lot of electricity gets converted to heat. And this is how you get light. Okay, now LED lights work kind of different. They don't produce nearly as much heat, but this is the basic idea. Now, so in a series circuit, the reason why they get dimmer is because each light bulb has resistance, and then the total resistance is the sum. So for example, if each light bulb has a resistance of 10 ohms, if R, no, actually not 10 ohms each. If R1, for example, is 10 and R2 is 20, then the total resistance for my circuit is actually 30. Now, think about then what we see and how this makes sense. What we see is that the light bulbs are dimmer. And that means that the current is lower. Now let's see that with a calculation here, okay? So imagine we have two light bulbs. One has a resistance of 10 ohms and one has a resistance of 20 ohms, okay? So we know the total resistance is 30 ohms. What would be the total current going through the system if the voltage is 15 volts? Well, remember, current is V over R. So the voltage of the total system, I mean the battery, is producing about 15 volts. The total resistance is 30 ohms. So then the current is 0.5 amps. So the current is going to be reduced because there's more resistance, which makes sense because if you look at your magic triangle, V, I, R, this is V over R. So if R gets bigger, then I gets smaller. So in a series circuit, the current goes down because the resistance gets bigger when you add things in series. But in a parallel circuit, so when we come back on Monday, we'll talk about number 8 and 9. We'll do some more, and we'll review this and we'll do some more. But if you look at number 9, not number 9. So if you look at the next question, which is resistance in parallel, well, in a parallel circuit, things look like they're brighter. So not dimmer, brighter. It looks like the electrons are actually moving faster, having an easier time. And that's because in a parallel circuit, the resistance is the sum of the inverse. Now, let me explain that, okay? The sum of the inverse is 1 over the total resistance is the sum of 1 over each resistance. So we'll look something like this, and so on. So let's imagine we only have the two light bulbs, and one has a resistance of 5 and 20. So in a series circuit, those two light bulbs, if they were in series, right, the total resistance would be 5 plus 20, which is 25 ohms. That would be if they were in series. But if they are in parallel, then the total resistance is the sum of the inverse. That would mean that 1 over RT is 1 over 5 plus 1 over 20. Now, when you do that, you get, well, you can't add these yet because we need a common denominator, but 4 out of 20 is the same as 1 out of 5. So that gives us 1 over RT is 4 plus 1 is 5 over 20. And then what you do is you flip it, okay? Because you don't want 1 over RT, you want RT. So what we do is we flip it. So if I flip this upside down, it becomes RT over 1, or just RT. And then I have to flip the other side. That becomes 20 over 5, which is 4. Okay? 4 ohms. Now look at that. Two in series, a 5 ohm and a 20 ohm resistor give you 25 ohms of resistance, but these two in parallel give you 4 ohms of total resistance, which is less than even the smallest resistor. So let's just do one last question together and then we'll call it, okay? So for example, if I have two light bulbs that are in parallel, so they'll look like this. So imagine this is my parallel circuit. Here's my battery. Okay, there's a parallel circuit. What would the total resistance be if they were both 10 ohms each? This is easy because they have the same denominator, so I can just add them. Now I just flip them. So I flip this one, it becomes RT over 1, and then I flip this, it becomes 10 over 2. So my total resistance then is 5. Again, you'll notice that the total resistance is less than the individual resistance. And again, because Ohm's law, I is V over R. If the resistance goes down, then the current goes up, which is the exact opposite of the series circuit. Okay, so hopefully that'll help you when you're working with the circuits, these concepts. When we come back on Monday, we'll review this and we'll do some of the questions that we did not look at. Okay, again, to help you with the circuits, but also there are questions just in general on Ohm's law in your CPT. Okay. All right, so let me, I guess we can stop there.